but okay. Okay, so welcome back. First of all, I would like to thank the organizers for having me here. It has been a very nice workshop. And going in line with the previous talk, we would like to continue our explorations of the origin of neutrino mass in some dark alleys. So yeah, the basic question, it's again just a continuation of the theme of the first talk of today from Alexei, that is, the basic question that we want to understand is that whether the nature of neutrino mass can be dynamical. Put it in a very layman's term, can the neutrino mass vary as a function of redshift? This is not a new question. People have tried to probe them from a model-dependent perspective or from a model-independent perspective, just by looking at data from cosmology, from baryon-acoustic oscillations, something that we heard a lot in the last week, even from using data from type 1 supernovae. And with some people in the audience, we have also made some predictions of how one can use the DSNB as well to probe this kind of a mass-varying nature of neutrinos. So the thing that I would like to motivate today, as already again has been pointed out, that in principle, this can arise due to neutrino coupling with ultralight dark matter. Now, what is ultralight dark matter? Let's spend some time to understand what do we mean by this. Now, as theorists, we love to play around with dark matter. There is this entire range, this almost huge stadium of masses that is accessible to us, from all the way up to 10 to the minus 22 eV to solar masses and tens of solar masses. By ultralight dark matter, we would essentially be focusing on masses of dark matter which is less than 1 eV or so. So these are non-thermal bosonic fields. Fermionic fields can also be accommodated, but there are other issues that one would have to cook up to avoid phase space problems. So we are dealing with ultralight bosonic non-thermal fields which have less than 1 electron volt masses. Typically, one example of this would be fuzzy dark matter that was invented in the early 2000s to solve some small-scale structure problems that existed in cosmology. The idea of this model is that dark matter has a wave-like nature. It's extremely light, so it has a very large de Broglie wavelength. And this wavelength is roughly of the order of galactic scale. So within a galactic scale, this dark matter would roughly behave as a wave. And outside, it just behaves like your standard cold dark matter. And it was shown that for usual choices of parameters and stuffs, one can do basically solve or minimize some of these small-scale structure problems with this kind of a fuzzy dark matter model. But for the purpose of this talk, we would not really worry about all these problems. We would just deal with light dark matter. One question that we want to answer is how do we produce these ultralight dark matters? It's usually expected that these kind of ultra fields would be produced ultralight fields would be produced coherently. One popular mechanism would be this so-called misalignment mechanism, which has been used a lot in action scenarios. In this case, the field, this ultralight scalar field is stuck in some potential well, which is given by its mass. And as the temperature of the universe goes down, this field is stuck in some initial condition, and this initial condition is set by some initial values that you want to set by yourself. And this is stuck because of some friction due to this Hubble term. Now, as the temperature of the universe goes down, the Hubble friction goes down, and at some point this mass term dominates, and this leads to the field oscillating about its minimum. And then the field can basically redshift like non-relativistic matter, and in this case, this can act like a dark matter mechanism. Mathematically, one can describe this sort of a field by using what we call a Glauber-Sudarshan state or a coherent state. This state, as Alexei also showed, is basically given by an exponential of the creation operator acting on your vacuum. So these are states which are minimum uncertainty states. These are eigenstates of your annihilation operator. And the very interesting property of this state is that if you take a state like this, take your classical field, take your quantum field, scalar field operator, take the expectation value. This looks almost like a classical field like this with some amplitude. And the amplitude depends on the density of the particle and the mass of the particle. There would be some fluctuations, but these fluctuations typically decrease as the number density of these particles increase. So the nice part is that as the field starts rolling, you can see this, it's stuck, and at some point it oscillates, and then this can be treated roughly as a classical field with some phase which is given by the mass and the velocity of this field. Sorry, what? This is some weight factor. So you can, in principle, take it to be identity, or you can attach a certain weight with the different momentum modes. So you're integrating over the different momentum modes. Yeah. So this, you can, in principle, take it to be a delta function at 0 also. It's your choice. Okay. So let's just do some simple back of the envelope estimates to understand that what are the properties of these fields. As I said, this field, because it has a light mass and we want it to be dark matter, so the velocity also has to be within a certain value, typical of the dark matter velocity in our surroundings. The de Broglie wavelength turns out to be very large. It's of the order of 1 kiloparsec or so for these values of masses. One can immediately calculate the number density of these particles and the total number, and it's huge. So for a mass of around 10 to the minus 22 eV, in a given volume, this number can be as large as 10 to the 90. This is why one can actually use a classical approximation, because the fluctuations are usually given by inverse powers of n, and this is almost negligible once this number is very large. This field, of course, has a modulation period which is given by this, and rough numbers are like for values of 10 to the minus 22 eV, the modulation period is around 1 year. Since we are dealing with dark matter, one can drop this part out here, because dark matter is mostly non-relativistic, and then treat this field just as some cosine variation with some amplitude. And this is what we are going to take as our starting point. Now, the question that we want to ask, and many people before have already asked, is what happens if you take this dark matter, which is already a very non-interacting species, and you take your neutrinos, which are also quite uh, inert by themselves, they only interact through weak interactions, and you make them talk to each other. Let's just write down a simple Yukawa coupling of this form with some coupling, and then you substitute this expression for the field. You can immediately see that this acts like a mass term. So if you remove this part, this contribution acts like an effective mass term for the neutrinos. And you can put in your standard numbers. So for a mass of around 10 to the minus 18 electron volt, this contribution is like this. And then that means that as soon as you choose your couplings low enough, let's say less than 10 to the minus 15, this can give an order 1 electron volt contribution to the neutrino masses. So you can basically have a model where your neutrinos have a vacuum mass, and then you can also have some mass, effective or refractive mass, that comes from interaction with this classical field. And of course, because there is some time modulation in this, one can expect a very, very rich phenomenology from different oscillation experiments, solar neutrinos, atmospheric neutrinos, and so on. And this is something that has been addressed in all these papers through this kind of a phenomenological coupling. This is very nice. One can look for these modulations. However, this comes with a catch. For all these nice models, always cosmology is something that comes and spoils the party for these phenomenological models. One needs to remember that dark matter, being non-relativistic, redshifts in the early universe, and it redshifts with roughly as the third power of, the energy density redshifts as the third power of the redshift, which means that the amplitude would redshift as 3 over 2. Now, if you couple that to neutrinos and you ask it to give a mass, that also means that the neutrino mass starts growing in the early universe. So if you are currently here and you go back in the universe, your neutrino mass will also start growing with the dark matter density. Of course, your dark matter density would become constant at some point, and this is the point where, as you go back in the universe, it again gets frozen by the Hubble friction. But that point is set essentially by the mass of the field. But up to that point, your neutrino mass would grow. And we have strong constraints on the sum of neutrino masses at different redshift intervals. So let's say you assume that the contribution to neutrino masses today is roughly of the order of the atmospheric mass square difference, square root of that. And then you let it redshift, then you see that at the redshifts of matter radiation equality, which is roughly 3000, the mass contribution is already 10 electron volts. And this is not allowed, because this spoils observations of sum of mu that we have from CMB and structure formation, something that we heard a lot about also last week. This number is much smaller. From CMB, it's around 0.1 or 2 EV, and if you take baryon acoustic oscillations, it can get even smaller. So this model is definitely not cosmologic friendly, and one needs to cook up other ideas to address it. One idea would be the idea of refractive mass that Alexei talked about. You introduce a new fermion, you make dark matter couple to neutrinos and this new fermion through a Yukawa coupling. In this talk, I would talk about another way of going around it. In this talk also, I would have a new fermion, but then instead of having a cross coupling between dark matter and the new fermion and neutrinos, I would make ultralight dark matter coupled directly to these sterile neutrinos. So this doesn't talk to active neutrinos directly, but it talks to some sterile neutrinos through this kind of a coupling. The nice part is that because it talks to sterile neutrinos, and this sector is almost untouchable in the in our experiments, so you can hide all your bounds through this. But then you could also get some contribution of this mixing to the active sector just via mixing of active neutrinos with these sterile neutrinos. And we want to see with this whether one can solve this kind of an issue. So you take this simple setup, take a simple two-flavor problem. You can diagonalize your mass matrix. This is what it would look in the flavor basis. You have the mass eigenvalues, you have this matter term, the dark matter term in some sense, and then you diagonalize. And this is a simple thing, and it can be done analytically. There are some interesting limits that one needs to look at. So let's say we are in the limit when this the amplitude of this field with the coupling is quite small. So it's much smaller than the sterile neutrino mass. Then you can show that both the active and the two mass eigenvalues essentially grow linearly with this term. Now, as you go in the early universe, G5 starts increasing. You reach a point when G5 starts becoming larger than M4, and then you can do some series approximations and show that something interesting happens. So M4 still keeps on growing, but the lighter mass eigenstate has some constant term, and then there is a term which essentially gets killed off as G5 increases. This is somewhat similar to what happens in the seesaw mechanism, where you also have this constant term, and this is what is expected to save you. So you can do this whole system numerically. You can solve for this system. You ask for the lightest mass of these two eigenvalues, which would be the mass of your active state. And you see exactly this is what happens. As your G5 grows larger, you go in the early universe, it starts increasing. It reaches a turnover point when G5 is roughly of the order of M4, which in this case is chosen to be some value of 3 eV. And then it flattens out. And with proper choice of parameters, you can make it flatten out to values less than 0.1 electron volts or so, which means that this model is cosmology friendly, at least from these considerations of structure formation, because even if it increases in the early universe, it would flatten out as soon as G5 becomes large. But the nice part is, once you go to smaller values, you would have a contribution that grows directly with G5, and which means that the time dependence of these scalar fields would be imprinted on the time dependence of these eigenvalues. And then you can search for the effects of these time dependences and try to constrain this model. So the idea would be that this kind of a scenario can be constrained from all sorts of terrestrial experiments through the time modulation, while as you go in the early universe, you would try to constrain them from structure formation or BBN bounds and so on. And this is what I would be focusing on in the rest of the talk. I would be talking about some constraints that arise from each of these experiments, from oscillation experiments, and this is going to answer one question that was asked in the previous talk about time modulations. And I'll also talk about some other experiments which would be sensitive to this. And the nice part would be that for people who have been around since last week, there have been talks about all these experiments. So I would briefly touch upon those talks, and you can connect with what I am saying. So let's first start with neutrino oscillation experiments. As I said, we are in this regime where G5 is small. So in this regime, the main effect that you see is that you pick up this time modulation due to coupling. And this time modulation is what can be seen in oscillation experiments. Now broadly, if you think about it, there are three time scales in the problem. There is a time scale of oscillation, which is given by the mass of the scalar field. There is a time scale which is essentially the distance of flight of neutrino. So it's a distance that the neutrino travels divided by roughly the velocity of the neutrino. And of course, there is an experimental time scale, which is of the order of a few years. Now, depending on what is the hierarchy between these time scales, is the signal can be different. So one very fine-tuned scenario would be where you have the mass exactly ordered in such a way that it's of the order of the experimental time scale. And that means that as the experiment runs over a period of, let's say, 10 years, it would see some very slow modulation of the neutrino mass, and neutrino mass would show some very small time variation. This has already been searched in some experiments for solar neutrinos, for example, and I will talk about it. But this is, again, very fine-tuned. One can look at other scenarios. Well, for example, the oscillations are very rapid. So the time scale is such that it's much larger than the length of the time it takes to travel the distance, but much smaller than the experimental time scale, in which it means that as the experiment runs, you would have a lot of oscillations, and this would average out. So you would see some distorted neutrino oscillations. One can even go to smaller scales where this is comparable to this thing, and at this level, the oscillations start becoming relevant as the neutrino travels, and this you have to treat dynamically as a potential. So you have to incorporate this as a potential in your Hamiltonian, and you can't really use a simple classical field treatment in this particular case anymore. So I'm going to quickly show you some, again, just to highlight, these were checked in these papers already, and I'm going to basically present some results that were used in these papers. So some very, very simple idea of what can happen. So if you are in this average regime where this hierarchy holds, as I said, you would have a lot of oscillations, and the net effect would be a smearing out of the probability. So if you look at, for example, this quantity, the black line would be what you see in absence of any of these couplings. But then if you want to switch on the amplitude of these couplings, which is given by this thing, you see there is a deviation, and it starts, as the amplitude starts becoming larger, you see more of a smearing out of the probability, and this effect can be searched for in different experiments. You can even go to the dynamic regime, and in this regime, the treatment is slightly different because the time scales are different, so you have to treat it as a potential. And then you again see some sort of a distortion, but then distortion is statistically different from what you see out here, and it only resembles this when you are in the limit when tau phi becomes much larger than tau nu, so you go back to this limit. So you can show this that in that limit, these two scenarios are identical, but as long as tau phi and tau nu are comparable, you can see some distorted effects of this. And using this, one can put constraints on the amplitude and the masses of these particles from different experiments. So suppose you assume that the field couples to the solar sector, so then it basically affects your theta 1, 2 and delta m squared 2, 1. Then you would get you would get constraints from, for example, Kamlan measurement of delta m squared 2, 1. So anything above this blue line would be ruled out. Super K, for example, has looked for time variations of this angle theta 1, 2, and they have not seen any variations from a period of 10 minutes to roughly 10 years or so, and this region is ruled out. And then, of course, you have constraints from CMB. Anything above this region is already ruled out, because if you are in this region above this, then you increase the neutrino mass, and this some mu starts becoming problematic. Of course, all these constraints assume that the phi is your entire dark matter, and if that is not true, then these constraints do not hold. And you can get similar measurements if you couple it to the 3-1 sector, and then you can get measurements from Diabae or from T2K, and you can even make projections for Dune and Juno. For the supernova enthusiasts, you can also produce these scalars in the star, and then you can get some constraints just by making the star cool by producing these light scalars. So this is roughly what you would get from oscillation experiments. But there are other features, other experiments that can give you stronger probes of this. One example would be beta decay experiments. So roughly this is I would be focusing on Catrin, which is one of the more popular beta decay experiments that we have out here. And this is roughly a poor man's version of what Catrin looks like. So you have an experiment where you have a tritium source, it beta decays, there is some retarding potential out here, it kills away all the electrons, and only electrons near the endpoints are what goes into the spectrometer. And depending on whether neutrinos have a mass or not, you would see a deviation from this endpoint. So this deviation from this endpoint is essentially characterized by this quantity, which is this effective mass square, which is basically a combination of the mixing matrix square times the vacuum mass square. And Catrin is sensitive to this particular quantity. So what does Catrin, let's first assume there is no coupling to dark matter and so on, and let's try to understand what Catrin is actually expected to see. So I show here basically a mathematical version of this cartoon. So this line, the colors are probably not very visible, but this black line out here, the one that you see out here, is what Catrin would see if neutrinos do not have any masses. But as soon as you switch on some masses, which is given by this 0.4 or 0.1 eV, you see a shift from this. If you take the difference from this black line, the main features that you see in Catrin are a kink-like structure and then a shift. So for example, as the neutrino mass increases, you see a kink and then a slight shift from 0. Of course, Catrin doesn't have any sensitivity to actually detect these things, but once sensitivity increases, maybe it can do a better job at this. Now, this is what Catrin would see in absence of any dark matter coupling. Now, let's say you switch on a coupling, you get this extra contribution. The nice part is that when you do a simple naive calculation of m beta square, you see that you get this additional contribution just from this coupling. And this means that what Catrin measures is actually this effective m beta square, which is very different from this quantity. This has two things. One, of course, there is a degeneracy. So you can basically mimic the effect of m beta square with g phi square. Secondly, as we heard in last week's talk by Maria, as well as we heard a bit today also, there are these tensions with cosmology where we have been asking the question that what if Catrin measures something and that is much larger than what cosmology sets a bound on. One can resolve this with this kind of a scenario because Catrin would essentially be sensitive to this quantity, which can be large, whereas m beta square can in principle be small. Of course, there would be effects of m beta square also, of this dark matter also on structure formation, but one can in principle resolve this scenario in such a coupling with dark matter. So this degeneracy is what Catrin can see, and this degeneracy is also relevant out here if you do like a scan in different parts of the parameter space. So for example, here we try to fit the data with varying m beta square and the coupling, and you can see this degeneracy coming up. So for every value of m beta, there are these range of values of g phi which can satisfy the same contours at certain confidence level. If you want to see how the best fit results would change, so for example, the black lines out here show what Catrin best fits are as a function of the endpoint energy and m beta square. And then on top of this, if you add this coupling and you let this coupling vary from some value, you get this entire region that is allowed. The interesting part is the endpoint doesn't shift that much. What changes are the effective values of m beta square that you are sensitive to. One thing that I want to mention is that when we were doing this, we were mostly using the Catherine run 1 and run 2 data. So we were mostly sensitive to negative values of m beta square. And there has been this whole discussion about how physical this is and so on, but this is what they're sensitive to. And of course, what we see is that this shifts to lower values. And in principle, you can satisfy the same thing with roughly the same endpoint values. But this degeneracy might actually reduce Catherine's sensitivity. Now, this is, of course, when this limit holds, and this is in the limit when sterile neutrinos are heavy or G phi is very small. This can also be relevant if you go to lighter sterile neutrinos, which are EV scale sterile neutrinos, which in principle are directly visible in Catherine. So these gray lines, for example, are essentially what Catherine would see with active neutrinos. This is similar to what I showed you last time. It sees a kink and a shift. But on top of that, let's say if you add a sterile neutrino, which has a mass of, let's say, a few electron volts with a largish mixing angle, similar to the ones that are preferred in these short baseline anomalies, Catherine would see an extra kink. And this extra kink would roughly turn up at the point of the sterile neutrino mass. So this is given by this dashed black line. Now, again, this whole thing is in the absence of dark matter. So Catherine can, in principle, set bounds on sterile neutrinos by this kind of a method. So it sees an additional kink and a shift. And from this thing, if they do not see it, they can put constraints on these masses and mixing angles. But then once you put an additional coupling with dark matter, things start becoming less exciting, because now this acts as an additional potential. And if you look at the mixing angle, what it does is it suppresses the mixing angle, the active sterile mixing angle in vacuum, so in matter. So essentially you have a certain active sterile mixing angle in vacuum, which is given by this quantity. But now, because your neutrinos are traveling in this dark matter background, you have to calculate the mixing angle in this dark matter medium, because the whole universe has this background, and what you're measuring is always this effective mixing angle. And this gets a suppression as soon as you increase G phi. And because of this, what happens is once you turn on this G phi, this kink starts becoming smoother, simply because now your mixing angle is smaller. So this extra contribution that you would get from these sterile neutrinos start becoming less and less important. And this means that Catherine will lose its sensitivity to sterile neutrino searches. This is not a good thing in terms of sterile neutrino searches, because they wouldn't be able to detect much. But for people who are interested in short baseline anomalies, this might be nice. And this is because, as I said, you would lose sensitivity to mixing, which means that to satisfy the same result, you would need larger values of mixing. So for example, if you do like a generic scan of what Catherine would be able to exclude in this M4 and UE4 parameter space, this blue line is what it would roughly see if you do not have any dark matter. But as soon as you switch on these dark matter couplings, then this starts shifting towards the right. So you have larger values of mixing angle which are allowed for a given mass. And this is important because this says that this in principle can allow you to open up some parameter space, in the sense that you're allowed to have larger values of the vacuum mixing angle in these things, which would be relevant for your short baseline anomalies. There are these weird features out here which I wouldn't discuss, and this essentially comes because in this analysis we set m beta square to 0, but if there are questions about it, I can answer later. So let's just quickly see what these short baseline oscillation experiments would tell us. And we already heard a lot about this last week, and we also heard about this from Ivan this week. And essentially, what from these short baseline experiments, we know that there is an anomaly. And the anomaly is that they have seen some excess events which they shouldn't have. They've seen some excess events and some deficits which they shouldn't have seen. And essentially, if you want to reproduce the region where they have seen these anomalies in this M4 square and mixing angles plane, this is roughly the black shaded line is roughly the region where you have seen it. Again, this is an older version of the plot. This needs to get modified. Of course, in the standard scenario, in absence of dark matter, there are constraints on this, as we also heard yesterday. There are on Monday, I think. There are constraints from solar data, because such large mixing angle already puts into tension these allowed regions from this gallium and reactor anomalies. Catherine can also kill out a large chunk of this parameter space, which is given by this pink shaded region. And of course, if you do not introduce additional interactions, you're already killed by Big Bang nucleosynthesis. So there are these extra radiation bounds which kills this entire region. Now imagine you turn on this new coupling, you again go back to this region, because you go back to this region where larger values of the mixing are allowed, because you're now suppressing your effective mixing angle in a dark matter medium through this kind of a coupling. So whatever is your vacuum angle, the experiments are essentially sensitive to this angle, which is the mixing angle in this medium. which means that to satisfy the same regions, you would have to go to larger values of your vacuum mixing angle. And essentially, all your contours start shifting towards the right, which are these larger values. So for example, if you slightly switch it on, it changes, and then as you make it larger, it changes and becomes even larger. It doesn't really help you in solving this tension because these constraints also start changing, but this is again a very simplistic analysis, and one needs to do a more serious analysis to see the effect of this kind of a coupling on short baseline experiments and so on. So yeah, a quick word on relic neutrino capture. We also heard a very nice talk on this by Stefano last week. And the idea is, again, there is this relic neutrino background, and there is this Ptolemy experiment which tries to detect it just by looking at relic neutrinos hitting on some tritium target, and then you're trying to look at the endpoint things. Now, again, this picture would change in the presence of this dark matter background, because now, again, the relic neutrinos are traveling in this dark matter background, and depending on what the couplings are, the signal that Ptolemy would see would actually be different from what it would see in absence of this background, simply because once you have this dark matter background, Ptolemy is again sensitive to the mass of the neutrinos, but the mass of the neutrinos now gets modified by this extra refractive contribution. So just to see what kind of an effect it has, so out here we show the rate of capture of in a Ptolemy-like setup as a function of the endpoint energy. So this red dotted line is what Ptolemy might be expected to see with a very small and very optimistic energy resolution. Of course, this is plagued by the beta decay background, that, for example, Catherine would see. And this dashed line is what the beta decay background is like. Now imagine you turn on this coupling, the effective masses of the neutrinos change. Now this whole thing gets distorted. So you actually get some leverage out here because the beta decay background starts shifting to the left hand side, whereas the Ptolemy spectra starts getting distorted. And this can allow an experiment like Ptolemy to also probe very, very tiny values of this coupling. Things get more difficult as you increase the resolution because the signal also becomes weaker and you don't get to see much of a distortion, but you still have some sensitivity. So for example, in the coupling and the mass of the plane, you can see that at 95% confidence level, Ptolemy can in principle exclude values of masses as low as 10 to the minus 18 with a coupling of around 10 to the minus 17. So this whole shaded region would be ruled out once Ptolemy starts operating. The differences don't change that much as you increase your resolution, because what you're essentially sensitive to is this endpoint region, and this region doesn't depend that much on the resolution in terms of this dark matter coupling. So you wouldn't get a lot wouldn't get a lot of advantage if you change the resolution, but you would in principle be sensitive to this kind of a coupling. Finally, one quick thing is also BBN, as I quickly discussed, that you might have some issues because you're introducing light scalars, you're introducing sterile neutrinos, and we know from an early universe perspective this is not good because you can in principle thermalize this before BBN, and then this can produce extra radiation and you can be ruled out by these constraints. But then again, it's this mixing angle that helps you, because although you have light sterile neutrinos and so on, but as you go in the early universe, this G5 starts increasing and it reduces the mixing angle. So even if you do end up producing them, you never thermalize them because you don't produce them enough because the mixing angle in this medium is not large enough. So as you can see, as this value of the coupling and the dark matter mass starts increasing, the contribution to delta ineffective starts going down. And if you are at a value of around 10 to the minus 18 EV and the coupling, so you take this product and this is somewhere around this, then you don't get a contribution of more than 1% to delta ineffective. So in principle, you can probe some regions of this with upcoming cosmological surveys, but you would mostly be free from other experiments. So yeah, this brings me to almost the end of my talk. I would end with one open question to the cosmologists out here. This is something that we found in this whole study and we don't have a clear answer to. And it pertains to this. So I talked about a scenario where the neutrino mass starts with some value. It increases as a function of redshift as the dark matter coupling increases, and then it flattens out at some point, right? And this happens because of dark matter coupling to your neutrinos. Now imagine as a model builder, you come up with a scenario, and I'm not going to justify how you can come up with it, it's a bit stretched, but you come up with a scenario where only one mass eigenstate picks up this dynamic mass. So you have this mass ordering, let's say I play around with a normal mass ordering, and I couple the dark matter to this new 2 state, and I let this evolve as a function of redshift. This grows, and then at some point it gets cut off, but that means that at some redshift, which can be large, like larger than 1000 or so, but this depends again on what parameter you choose, your effective M2 becomes larger than the masses of nu3 and nu2, which means that you end up changing the ordering. You don't go to the inverted ordering, mind you, but this is a different ordering where at larger redshifts you have nu2 is larger than nu3 is larger than nu1, even though today you start with the normal mass ordering. And this kind of a scenario, to the best of my knowledge, has not been tested in cosmology, and I'm not even sure if it can be tested in cosmology, because my understanding is that cosmology is only sensitive to the energy density in neutrinos through the sum nu parameter. And as long as you are satisfying that, you would not really be able to tell apart which part of what mass ordering the neutrinos have. But I would be happy to know if there are other ways of test this. But yeah, so with this, I think I'm running out of time, so I'm going to conclude. So the main takeaway message is that in principle, one can couple active neutrinos to ultralight dark matter, and this leads to very, very interesting phenomenology. But then this is cosmologically very difficult to accommodate, because dark matter gives a mass to active neutrinos, and this active neutrino mass starts growing, and this is not allowed. One way out is to couple this ultralight dark matter to sterile neutrinos and then allow the mass term to get into the active neutrinos via mixing. And this is good because this can be cosmologically safe, and as a result, this can allow you to get rid of the bounds that come from CMB and structure formation. And at the same time, this can give you all these interesting probes that one can have in different experiments, and leave us with some open questions which we can probably probe with our upcoming cosmic surveys. Yeah, so with this, I'll conclude. Thank you.
Thank you for this interesting talk. Okay. Could you help, please? It's up there. Okay.
Hi, thank you very much for. Now?
I can hear you, yeah.
Okay. Change of the hierarchy, right?
Yes. Yes. This one, right? So if I understand, you want to see what happens right out here. So
Yeah.
for these choices of parameters, like we took mass of phi to be minus 19 or minus 18 electron volts, this thing starts changing at redshifts larger than 1000. So before CMB, I would say.
Yeah. I mean, to measure this from cosmology, to detect this is basically impossible.
That's what we all, but so even if we can make it shift at earlier redshift, it's a bit difficult in this model. Is there any? So
well, yeah. At earlier redshift, if you have a measurement of the power spectrum,
yes.
very, very precise measurements of the power spectrum, for instance, 21 centimeter surveys, right, which can you give a measurement at different redshifts of the power spectrum, a very precise one. Maybe you can see the kinks in the power spectrum and see a change there, you know, I mean, from one hierarchy to the other, okay? But this should happen at distance,
very low redshifts, I see, okay.
I mean,
yes, yeah, because that probes like redshift less than 6 or something, right?
Yeah.
Okay.
Well, no, they can go higher, but I mean, not 1,000, of course.
No, for sure, yeah, okay.
Okay.
So yeah, the basic question was if the mass ordering actually changes, and if one can come up with a scenario where, let's say, it's inverted ordering in the early universe and normal today, is there a way that cosmology can actually tell us, provided the sum of mu is still within the experimental bounds?
Yeah. Okay. So thank you.
Other comments? Questions? Michu.
So, like, I also like have question like this, like if you consider the case that like only one neutrinos obtain some mass in the early universe, maybe like the signal in Ptolemy experiment also significantly change. I guess one? Ptolemy experiment. CNUB capture, because like for example, the heavy neutrino will obtain more kinetic energy at the end of the day.
Yes, so it depends again at what redshift you are looking. So at this point, yes, if you do this kind of a change, Ptolemy would be sensitive, but you would need it again at slightly lower redshifts, I would say.
Also, like, could you please remind me, like in this case, what happened with the ineffective?
Delta ineffective? Delta ineffective is not very useful out here because what you're measuring is the mixing. So let's say you want to produce sterile neutrinos from active neutrinos via the standard, Dodelson-Wittrell-like mechanism or so, by mixing and collision and so on. That depends on the mixing angle in this medium, and the mixing angle gets a suppression factor from this coupling. So as you go in the early universe, this starts becoming large, which means that the mixing angle becomes small. So for example, if you take a value of G phi of the order of, let's say, 10 to the minus 7 eV, then the contribution of delta N effective is like less than 1%. And so this is already quite safe. Only if you go to large, like smaller values, then it can be important, because then this suppression is not large.
You're assuming like a CP needle field for the fire, so the misalignment product. Is it actually possible?
For, sorry, what was your question again? We don't really care much about that, but in principle,
And then you're using misalignment, so is it actually possible?
so I don't know the answer to at the top of my mind, because in principle we just want this phi to behave like a classical field, and misalignment is just one mechanism. So of course this is true for an action like scalar or any light scalar, but
Usually you do the axiom because you have to as a shift symmetry
yes.
to protect the sharpness.
Yes, so but that is one way. You can put some additional symmetry. You can assign some sort of a lepton number to this and assume that neutrinos are Dirac and lepton number is not violated. And then in principle, the moment phi gets like a non-zero mass, a large mass, or so, then you can have issues with that. So in principle, there is no restriction on what symmetry you put. We don't want it to be an action or a shift symmetry protected phi as well. That can be one mechanism of doing it, but that's not the only one. I can imagine. Yeah.
Other questions or comments? No? Okay, if not, let us.
Thank you.